So they told you to watch Syntagma when you want to learn Houdini, huh? So you want to switch to Houdini or simply add it to your toolkit and you don't know where to start. Look no further. This is your quick start to understanding the basics of Houdini. We assume you know a bit of 3D and have a broad understanding of how 3D CGI works, having worked in traditional apps like Blender, Cinema 4D or Maya. And I personally struggled massively when starting Houdini. It actually took me 3 attempts to finally stick with it. In my opinion, the first 6 weeks will be the hardest. So keep this in mind. With Houdini, you're learning a totally new language. A language which isn't like anything else you've seen in your other DCCs. In many ways, Houdini is actually more similar to an IDE, an integrated development environment for 3D content. And I'm saying this to motivate you. When you're starting to learn Houdini, you will hit walls. That's absolutely natural. Just try not to get too angry and not too frustrated within those first weeks. Because hitting a wall oftentimes means learning something. So where did Houdini come from? Well, it turns out it's not like your standard DCC, your digital content creation app. Houdini is more about the underlying principles. So you will have a lower chance of getting a shot done by just hitting random buttons and trying to wing it. Instead, if you get some idea about the underlying basics of 3D and CGI, that's really great, and it'll help you a lot when you're starting out in Houdini. Houdini, in my opinion, started out basically as a toolkit for building tools, in turn to build 3D content. However, by now it's been augmented so much as that it covers all the bases of your traditional DCC app, and even more. However, it's still particularly useful and well-suited to building procedural, generative tools. And thus, you might still want to keep your standard DCC app on the side to take care of most of the mundane tasks, such as hard surface modeling or rendering. And don't get me wrong, we will cover rendering in those 5-minute intros here. It's just one of the last areas that I personally touched inside of Houdini. So you're firing up Houdini for the first time, and you're confronted with this massive program. What is it? Well, to understand it better, let's look at its individual modules, the so-called contexts. After starting Houdini, this is what you're confronted with. The standard layout in what's called the build desktop. So if you're in some weird other configuration, you might want to head up here and choose build. As I mentioned, Houdini can be seen as an operating system, stringing together different modules, which are called contexts. And the main area where you can switch between those contexts is here. And this area here is quite important, because that's the area where you're building your node trees. And above that, you have your parameter area, where you set up parameters for the individual nodes. Also, you got your main viewport with the usual Alt navigation, so holding down Alt and pressing the left mouse button rotates, pressing the right mouse button zooms in and out, and pressing the middle mouse button just translates. But let's get back to these modules here. So this is how you could look at Houdini, being an operating system stringing together those individual contexts here. And within this operating system, each of those contexts would be a certain application, an app, working on a certain type of data. For example, the IMG context would work on two-dimensional images, or the OBJ context would work on geometry data. And there are quite a few contexts here, because Houdini is able to work on quite a few different types of data. However, in our 5-minute intro tutorials, we'll be focusing on these 3 contexts here, OBJ, mat, and out, with OBJ standing for the context that's working on geometry data. So what we're going to do in here is procedural modeling, geometry building, setting up lights and cameras. Then there's the mat context, which is working on material and shader data. So we'll set up materials and shaders in here, which then will render using the out context, which works on scene descriptions for rendering them. And within each of those contexts, those individual applications, you're going to use nodes to build a node tree to tell those applications what to do with the data running through them. And up front, I just want to mention a few special nodes and a few special subnetworks that exists within a geometry network in the OBJ context, namely the simulation and the particles, which live in a DOPnet. DOP stands for dynamic operators, and the POPnet, which stands for particle operators. And by this icon here, the same icon, you can see those are basically the same kind of subnets here. So those will be used to build dynamic simulations, enabling you to simulate rigid bodies, soft bodies, smoke, fire, and hair, for example. And also, as we are using individual nodes that are mini programs to manipulate data within these individual contexts, there's another low-level way to create those individual nodes, which is using scripting, either through VOPs, VEX operators, which is a visual kind of scripting using nodes, or VEX, Houdini's built-in language to build those nodes and to manipulate data, which is a C-style language. And the nice thing about both VOPs and VEX is that they are not tied to the OBJ context, but they are available in most other contexts as well, being able to manipulate other types of data, as for example two-dimensional images or sound waves. And VOPs is a visual node-based representation of VEX, so anything that can be programmed in VEX can also be set up using nodes in VOPs. So do you have to learn VEX in order to be able to use Houdini? The answer is definitely no. However, if you want to use Houdini's full potential, I suspect there might be no way around VEX. as in my opinion is the single most determining factor that unlocks most of Houdini. And also, in contrast to most other operators, vex works in most contexts. So most of those contexts we see up here have some sort of a vex scripting area. So learn vex once, and you'll be able to use it all throughout Houdini. That being said, in our 5-minute videos, we try not to use vex as far as possible, not to scare you away. If you like what we're doing and want to support us or want to gain access to more in-depth courses, we're super happy. In the next 5 minutes I want to build with you the geometry for this, which was the very first thing I built back when I started 3D and Cinema 4D. Shout out to Grayscale Gorilla. So let's dive into Houdini, and as we want to build geometry, we are working in the OBJ context. And what we want to do is drop down a geometry node here by pressing Tab, which brings up this menu. And yes, you could go through everything here and just select the geometry, but Houdini's search function here is very powerful. So I'm just going to start typing geo and hit enter. Then I've got this hovering node here, hit enter again to drop it down. So that's my geo node in here. And inside this node lives a tiny program that generates some geometry, which is then displayed in the scene here. And currently this node is empty, so there's no tiny programs executed in here and no geometry is created. So let's dive into this geo node by hitting enter or I. And again, you can see this is empty. And for example, I could press tab again and start typing sphere, hit enter twice and drop down a sphere. And now inside this geometry node, I've got a program executing here that generates this sphere, which now is a primitive type. So it's a perfectly round sphere. And we can change its type up here in the parameters. This is where I can select and change the parameters for the selected node here. So I might want to set that to a polygon and increase its frequency to increase the subdivision, like so. Let's say I randomly want to place other spheres onto this sphere. The way you typically do that in Houdini is using copy to points, this one here, and let's just create another sphere, highlight this. So this is the visibility flag. And within your geometry container, there can only be one node that is visible. And this is actually the node that will be output to Houdini as a result of this whole program that we're building in the geo node. So let's scale this sphere down here a bit and set it to be a polygon as well. And now we can set up our copy to points. So this takes in two inputs, the target points to copy to and the geometry, which we're going to copy. So we want to copy this small sphere onto the points of this bigger sphere here. So let's highlight the copy to points. And you can see we very regularly copied this sphere onto those spheres' individual points here. And if we dial back the frequency of the big sphere here, we can influence how many individual copies of that small sphere are instant onto that. However, that's a bit too regular, so let's just highlight this sphere and again increase the frequency and drop down a scatter node here. And by the way, those tiny nodes we're stringing together here are called SOPs for surface operators. And those lines that form between those nodes are data flow. So in this case, it's geometry data flowing through our tiny program that we're building. So what the scatter sub does is it scatters points onto a surface. In this case, 1,000 points, which when we highlight the copy to points is a lot. So let's dial back the actual point count like so, and maybe increase the frequency and thus the subdivision of our spheres that we're instancing on here. Alright, neat you might say, but I want to have points inside that sphere as well and not on the surface. And for that, the usual workflow in Houdini is to convert that sphere here, which just is a surface, into a volume. And a really quick but also a legacy way of doing that is using a node called ISO offset, which I typically only use in this workflow. So what this does is it turns that sphere into a volume. And by increasing the sampling division here, I can increase the volume's resolution to say 60 or 64, and then pipe this into the scatter node. And now we're scattering the points throughout this volume here. So when I highlight the copy to points here, you can see I've got points distributed also within that spherical volume. The last thing I want to do for now is change those individual spheres' sizes. And I'm going to do that by using an attrib randomize, which I'll wire in after the scatter node here. And by default, it's set up to randomize an attribute called CD. That's the color diffuse. And you can see the results of this, those differently colored spheres here. However, I want to change this, not to randomize CD, but some attribute called pscale. And we end up with this. Let's dial down the dimensions, because this is only a float value. And let's increase the minimum value to say 0.3 and the maximum value to 1.5. So we end up like this. Finally, just for good practice, I'll append a null to that here. And if I hit Shift Enter, I can directly attach this null to the last selected and highlighted node. And I'm just going to call this node out here. So that's the output. So that's our very first, very tiny network we built in Houdini. If you like what we're doing and want to support us or want to gain access to more in-depth courses, we're super happy if you decide to support us on Patreon. So at this point you might be asking yourself, what the hell did I just do here? Let's just save this, and I want to talk about these attributes that I mentioned. So one way of displaying what our program does here is this, our viewport, the most useful and intuitive way of displaying 3D data. However, there's also a tab up here called Geometry Spreadsheet, and when I highlight this and highlight a given node, I can see the data that we're generating using this program here. And in our case, we are generating a bunch of points, and they only have their position in X, Y, and Z. And by a bunch of points, I mean many. But also, we are generating primitives, and also, those are quite a lot. And primitives in our case are those individual triangles, those polygons here. So back to the geo spreadsheet. And to define primitives, a primitive needs to have vertices, which we can display here. And also, the whole geometry stream as such has detail attributes. In this case, it has none, but the whole geometry can have attributes on itself. Another way of displaying a rough info about these attributes is to middle mouse on a node, which displays this here, or to just hover over a node and hit the info button here. So you can see we've got around 44,000 points, 88,000 primitives, 264,000 vertices, and 88,000 something polygons in here. And we've got one point attribute called P, which is the position. So this is Houdini's help file to illustrate a bit further what we're talking about here. When we're working with geometry data, this is the data we're typically working with. And this data stream can store individual values in different places. So it can store values on the detail, which is a single value per attribute for the whole data stream. Then it can have primitives and primitive attributes, and those primitives onto which we store those primitive attributes typically are something like polygons, polylines, or NURBS. And those primitives are typically defined by assigning vertices to a primitive, which are these purple triangles here. And those vertices, in this case, define which points make up a given polygon. And finally, we have those points, which are positions in space, and they can also store data on themselves. And Houdini having points and vertices is something that can be confusing when you're coming from other software tools. But it's an important distinguishing. But it's important to understand what's the difference between those two. So a vertex in this case is a data structure that assigns a point to the corner of a polygon here. An analogy would be this. This triangular solar sail here would be our polygon. And those pillars here, at least the top of those pillars here, would be the points in space. Those holes, or those strings that attach the sail to those pillars here, are the vertices. So one pillar can have multiple sails attached to it. For example, it could have another sail attached on this side. And that's exactly the same as points and vertices work in Houdini. So a single point can be used to specify multiple polygons, just by assigning it to a given polygon using vertices. And when we highlight this part of the geometry stream and go to our point display here, you can see not only do our points have their position in X, Y, and Z, but they also now have a value called p-scale. An attribute called p-scale, which has a float value ranging from about 1.5 as its biggest and 0.33 as its lowest value, which we set up with this attrib randomize here. So when we select the geostring before that, we can see the points do not have that p-scale attribute, and after they do have that. Why did I call it p-scale, and where did I know that from to call it p-scale, to influence the scale of the spheres that we're generating? Well, there's a list with what's called template point attributes. And if you use an attribute with a name on that list, copy to points here will take care of using that attribute to do something. For example, to scale, to orient, or to color your individual copies, which is something that we want to do in the next tutorial when we are going to render out this image. If you guys like what we're doing and want to support, so when it comes to rendering this, as usual in Houdini, there are multiple ways. What I want to do in this case is set up a color on those individual spheres here by using another attrib randomize. So I'm going to drag down those few nodes and drop down another attrib randomize, which I'll wire in between here. And immediately you will see I've got those randomized colors. However, I want to be able to dial those in. So in the attrib randomize, I want to tweak my random distribution. And there's one mode that is called two values, which allows me to dial in two discrete values, which then are randomly assigned to each of those points that are fed in here, onto which we're then copying those spheres, which in turn get colored by the points color. So let's maybe set up one orangey color here, something like that, and more like a blue color in this one here. Something along those lines. Next, let's go up one level by hitting the U key, and we're now back on our OBJ context. So in order to be able to render this, we need a camera and a light. So by control clicking on the camera icon up here, I will create a camera at my current position in the viewport. And when I start tumbling and moving around in this viewport here, you can see we're losing this camera. It's staying at its original position. So let's reselect the camera up here and look through camera 1 again, but this time enable this lock and lock it to the position in our viewport. So when we tumble now, the camera moves with me and with the viewport. In that camera, under the View and Render settings and Sampling settings, I can set up my render resolution in View here, and also my focal length. I'm always a fan of a longer lens, like an 80mm portrait lens, so let's use that. And also, I'll need some lights to render this. And in my case, I want to make this easy and just use an HDR, so I'll control-click on the environment light, which is just going to drop down this env light here. I can select an HDRI, so I'll take this one and select one of those images here. Keep in mind that if you have multiple images with the same name and just an incrementing file number at the end, you have to maybe uncheck Show Sequences as one entry to be able to select those individual files that you want to select. I'll just take this HDR here, hit Accept, and after a short while it will appear in my viewport here. Maybe let's increase its intensity a tiny bit so it's a bit brighter, and then set up the rendering. And for that I'd like to reconfigure this interface here a bit. I'd like to close those tabs here, then pin the tabs that I have here, and then hit Ctrl and T twice to create 2 new tabs here. In the last tab I'll switch to my Out context, and I'm going to drop a Mantra node here, which will configure Mantra, Houdini's built-in rendering engine. And in here, under the Rendering tab, I'll set my engine to physically based rendering. There are other methods in Houdini for rendering, some of which have some advantages in special cases over physically based rendering. However, physically based rendering is what I use about 90% of the time, so let's stick with that. So far for now, I want to head to the second tab I created and switch this to the Matte context and create materials, shaders, to assign to our geometry here. For now, I'm just going to hit Tab and use the classic shader, which is Houdini's Uber shader. And in here, I want to set the base color to be all white. Otherwise, the shader is set up so it automatically evaluates the color we wrote into those spheres to color those. So let's assign the shader to the spheres in the OBJ context, where I'll select the Geo node, go to the Render tab, and in here, hit this button, and in my tree view here, select the classic shader I just created, hit Accept. Also, what I want to do is, again, unlock the camera from the viewport, move to the side a bit, and maybe add a background plane. So I'm just going to drop down a grid, which is Houdini's name for a plane, dive in there by double-clicking, hitting I or Enter, setting the plane's orientation to be along the XY axis, like so, and then going up again by hitting U. And now I'll wire this grid down below my camera, so it's now parented to the camera. And then I'm going to move it back, so it sits behind my spheres here, maybe like so. Alright, let's look through our camera 1 again, and let's go to our render view here and hit render. So I sped up the rendering portion up until here, because Mantra, to be honest, is not the fastest render engine out here. And the first thing I'll see in my converging image here is that I want to assign another shader to my background here. So I'm going to stop this, maybe make a screenshot for later. So in here you have a bar that allows you to switch between all those screenshots you've took. Go back to my scene view and go to the materials context and just copy this classic shader and paste it, calling this BG for background. And in here I want to dial back the base color to a dark blue. Something like this, a really dark purplish blue. And again, onto the grid here in the render tab, I want to assign this material. Okay, let's go back to our render view and render again. Alright, that's a bit better. So let's stop this, take a screenshot, and now you can see we're progressing here. However, I think we can do a bit better by tweaking a few things here and there, which we want to do in the next video. If you guys like what we're doing and want to support us, you might want to head over to our Patreon, and we'd like to thank all of our patrons, especially Refik Anadol, Chris Hebert, Important Looking Pirates, Encore VFX, Patrick Fillion, and Gearbox Studio Quebec. So, you already set up your basic rendering. However, you think there's still room for improvement. And I'd say you're right. So let's do that. The next thing I want to do is add some highlight behind those spheres here by adding a point light. So in my scene view, I will control click on the point light button, which again will create a point light. And that's a bit weird about Houdini, or actually it's kind of useful. So you're looking through this point light now, and if you hit the lock button again, you're able to reposition it by just moving around in your viewport. However, in this case, I do not want that, so the point light has been created at our camera position, and I'll just make sure that the tool handle here is checked and move this point light back behind our spheres here. Something like that. Okay, let's look back through our camera and maybe move that point light to the side. Okay, let's hit render again. Few things I'm seeing here. First, my background material is still reflective. and then the light might be a bit too bright. So let's stop the rendering, just for good measure take another screenshot here, and go to our material first, and in the background material, go to Reflect Base and uncheck Enable Base Reflection, and then let's re-render this. So that took care of this ultra bright specular reflection on the background. Let's make another screenshot here, stop this rendering, go to our OBJ level again, and maybe dial back the strength of our point light a bit, using the exposure here and setting that to maybe 5 instead of the 7 that we had by default in there, and hit render again. And now I'm going to compare this to my previous setting here, and I kind of like something in between, so maybe let's just take another screenshot and increase the exposure still a bit to 6, maybe 5.5. Yeah, I like this. Okay, screenshot this again. And although this is starting to look nice, I'd like to add a few things. First, I'd like to add depth of field. So let's get back to a scene view here and make sure the camera is unlocked and have a look at the scene from the side and set up the depth of field and actual focal point of the camera. So highlight the camera, make sure the tool handle is selected and hit Z while hovering over the viewport, which will bring up this gizmo here. And this is your focal point. So I'm going to move the focus back to the spheres here and dial back the actual plane that's in focus. So everything that's between those cones should be in focus. So a really tight depth of field here. Let's go back to my main camera. For the depth of field to actually show up in my rendering, I have to go to the out context and in my mantra node, configure mantra to render depth of field by just checking enable depth of field in the rendering tab here, like so. Okay, let's hit render again. And you can see that, as I mentioned, Mantra is not the fastest engine on this planet, and B, there are spheres now that disappear in this depth of field, in this blurry bokeh down here. Next, when I look at this image, it starts looking nicely, admittedly. However, it's a bit dark, because it's missing global illumination. It's missing diffuse bounces. And that is because Mantra by default is not set up to take into account global illumination, but it's really easy to do so. So again, in the out context, with the Mantra node selected, let's maybe draw this down here and go to the Limits tab, which is in the Rendering tab here. And within the Limits tab, you can dial in how many reflection, refraction, diffuse, subsurface, or volume bounces the render engine actually does. So let's just screenshot our current state here and increase our diffuse limit to maybe 3 diffuse bounces. And immediately you can see that the image got brighter because we now got more diffuse light in the scene. So maybe we want to dial back our point and our environment light. But also you can see, especially in those areas here, that we are getting this nice diffuse interplay between those two surfaces. So yeah, in the OBJ context, maybe, just maybe, let's dial back our point light again to 5.0 and go back to the out context and configure Mantra for final rendering. So currently we're in this preview mode where we have buckets all over the place just trying to give you a coarse preview image. You can disable this mode and switch to final bucket rendering by just clicking this button here, which is now preview mode unchecked, and we now have this spiral rendering mode. As you see, this does not converge well. So in the out context, in the Mantra node, let's go back to the sampling tab, which is under rendering, and increase our samples. And without going into too much detail here yet, you've got primary samples, which is the pixel samples per pixel, and secondary samples, which are dialed in adaptively between the minimum sample count of 1 sample and the maximum sample count of 9 samples, depending if this noise threshold here has been reached or hasn't been reached. However, as we have lots of depth of field in this scene, depth of field usually is determined by the pixel samples, so let's increase those to say 12 by 12. And immediately you can see that the noise level in the depth of field went down, but also that our render times increased massively. And I'm not sure if I mentioned this, but Mantra isn't the fastest engine on this planet. So when we look up here, the ETA, the estimated time to arrival, is about half an hour for a 720p image. But well, that's the beauty of rendering physically based images with Mantra. If this at some point is finalized or converged, what you can either do is right-click in here and save the frame to your disk using a dialog that pops up when you click on this. Or if you don't want to use this preview window workflow here, stop the rendering and in the Images tab in Mantra, set up your output directory here by either selecting it with the file browser here or just using this expression. This is HScript, Houdini's other, more legacy scripting language, telling Houdini to render this into the folder where the project file sits, which is called $hip, then create a subfolder called render, and then create an image, which has the same name as your HIP file, the name of this output node here, and then a frame number with 4 digits. And then you're just gonna hit render to disk, and nothing much is gonna happen when you're just rendering out a single frame. So there's no status bar for a single frame. That only appears when you're rendering out animation. But when you open up your task manager, you can see Houdini is working really hard to render out this image here. If you guys like what we're doing and want to support us, you might want to head over to our Patreon, and we'd like to thank all of our patrons, especially Refik Anadol, Chris Hebert, So we rendered out our very first setup in Houdini, and I want to take this very moment to again mention how important attributes are throughout Houdini, and to show you their power and what they are capable of, and what in turn you are capable of with creating with them. Let's not display this grid here, and also just switch off the lights for now, and also in here, let's just uncheck light enabled. I want to dive back into our geo here, pressing enter, make sure our camera isn't locked to the viewport, and instead of scattering those points on which we copy spheres them, so let's highlight those points here. Instead of copying them onto a volume that we created out of the sphere here, I want to just flatly scatter them onto a grid. So I'm just going to drop down a grid, which is Houdini's lingo for a plane. Wire this into our scatter node here and highlight the scatter. And also, let's just prematurely select the handles here, the tool handles. So we can see this grid here. And this grid currently has a very coarse resolution of 10 by 10 polygons, which is fine for what you'd usually do with it. However, for the trick I want to show you, let's increase its resolution to say 100 by 100 rows and columns, so we have a more finely divided grid here. Let's just get rid of the sphere and the ISO offset by pressing delete. And before we do anything further, let's highlight the scatter sub and have a look at these grayed out options here. One of those options here is the relax iterations, which makes sure that the points are evenly distributed, and you can dial up the iterations. The more points you have, the longer this process is going to take in the end, so the default of 10 relax iterations usually is fine. And that just keeps the point apart and evenly distributed. And currently we're just uniformly scattering those points onto our grid. However, up here I can check something called density attribute, which in this case results in an error. So let's click on this error symbol here when hovering over the node, and we see the error is invalid point density attribute specified. It must be a numeric attribute, but can be a point, vertex, primitive, or detail attribute. So basically what Houdini is telling us, there is no density attribute currently on this grid here. So let's uncheck this again, and middle mouse onto our grid, and we see there's only one point attribute, that's the position of the grid's points. So let's create a density attribute, and in this case I want to be able to kind of paint in the attribute. So let's do that using an attribute paint node, which we'll wire in between here. And by default, when we middle mouse on this, the attribute we create here and paint in is called mask. However, under the attributes tab here, we can set the attribute name to be density, which is what our scatter sub expects. And now, when we set our view flag to the attribute paint node here and have our tool handle selected, we see this tiny gizmo here, which is a paintbrush. And by using the mouse scroll wheel, we can increase or decrease its size and then use it to paint something onto this geometry here. For example, an N for entagma. Let's just see if that did anything. Yeah, and if we go back to our main tab and reselect our tool handle, we can see the attribute we just painted in, with the areas where the attribute has a high value in red and the areas where the attribute has a low value in this purple blue here. So when we set the view flag to the scatter sub again and highlight this, and now check density attribute, we are now getting those points scattered in the areas where we painted them. And the nice thing about the procedural, generative, non-destructive workflow of Houdini is that at any given point in time, I can go back up here in the attribute paint node and adjust the areas and paint in additional areas. Let's just have a look at this. What went wrong here? Let's just undo this. Again, up here. Yeah, and repaint this. So now we can again select the scatter, and we see we're scattering points here. However, I want to get rid of that blob, so I'll undo this again, highlight the scatter, and then we're attribute randomizing the p-scale and the color as well, and then we're copying spheres onto those points. Another thing I want to mention here is that currently we have our sphere scaled down. So by default this should be set to 1. And instead we should adjust the sphere size using the p-scale value. So let's dial that back to say 0.05 and say 0.2. Like so. And if you have these truncated zeros, that's a rounding error for what the float value looks inside Houdini. So let's just click on this name here and it'll disappear. Okay, let's increase the number of points we're scattering in there by increasing the number of forced total count here, say to 150. and you can see these intersections happening, for example, here or here. And that is because we are manipulating the point's individual scale after we scattered it. So what we need to do after we set the p-scale here, and you can see those were the points that were intersecting, we need to relax them. We need to push them apart depending on their actual p-scale value that we've written on them. And we can do that using a node called point relax, which I'm going to wire in here, and I'll highlight it. And nothing much happens here, because this, the way it is set up currently in our node tree here, needs a geometry to which those points should adhere. So I will wire in just the grid that we scattered those points onto. And you can see now these points here have been pushed apart. Let's highlight our spheres here, and you can see Houdini took care of resolving those intersections by pushing those individual points apart. Let's just disable this node here briefly to show you the difference. And again, this is our slightly more complex flowchart of what we build, slightly more complex node tree, this time being able for you to paint the areas where you want points scattered and also relaxing them after we set the random p-scale value onto each point. What I like to do in those setups where you can dial in or strongly manipulate the looks of the setup, I like to color code those nodes. So by hitting C over your node view here, let's just give them a red color so everyone sees what's happening there, and that's where you can paint. So let's highlight the out. And in the next video, let's have a look at how we can use those attribute values that we just painted here to distort the underlying grid that we're using. If you guys like what we're doing and want to support us, you might want to head over to our Patreon, and we'd like to thank all of our patrons, especially Refik Anadol, Chris Hebert. So now that we know how to use and access or paint attributes, let's use this knowledge to build this kind of animation here. For that, I'm going into my setup, which is like this. So I painted an attribute onto my grid here, which I then use to scatter those spheres onto it. And this attribute here is called density. And what I want to do in the end is use the spheres that we scattered onto this grid using some sort of noise. And the most straightforward, easiest way of doing that would be to use a mountain sop, which will wire in after the density attribute. And the mountain sop just distorts your geometry, like so. And I can use those parameters here to dial in the noise that is used to distort the grid, maybe something like that. So if I want to limit this distortion to the areas where we just painted the density value in here, I could use the group attribute up here, the group field. And usually that's used to just type in a group's name, and then the effect of this node, in this case the mountain node, is limited to said group. However, in here we can also type in short expressions. So I want to check if my density attribute that I painted is above 0, so if it's bigger than 0. And we do that by typing in an at to access an attribute that's on this geometry stream that's piped into the mountain sop. Then the attribute's name, density. And now we want to check if it's bigger than 0.0. And if it is so, we apply this distortion here. So let's use that to then scatter points on it, and again use it as the geo to relax the points onto. And then when we highlight the out node here, we can see this is what we're getting. So if I want to animate this now, I'm running into a few issues. Let me demonstrate. Let's animate this using the Y offset, and either you could keyframe this by shift clicking in here, which would open up the keyframe timeline, and then alt clicking in here, setting one keyframe at the current frame, then moving this to the end of the animation, setting this value to maybe 2, alt clicking in here again, and then I'm getting this animation curve here, which I can then highlight and set to linear, like so. Let's just close this and reset this, toggle real time, and hit play. Now you're seeing a few issues here that I was mentioning. First, this is damn slow. Second, these spheres jitter around. Why is that? What we're doing here is we are distorting this underlying grid, which is running in real time. However, after that, we're scattering points onto this moving grid, which already slows it down a bit because we relax those points. And that also introduces this jitter, because in each frame we're scattering onto slightly different geometry, which totally messes up our point distribution in space. And as an additional factor, we post-relax those points afterwards, which again is slow, as you can see here, as it is cooking each frame, as the underlying geometry and the point distribution is changing, so we need to recook this relax, and also it introduces additional jitter. So what could we do instead? Well, let's get rid of this mountain here, reset this, highlight our grid with the painted density attribute. What I want to do is I want to move the individual points of this grid here along the y-axis. And I can easily create a vector, that is a directional arrow, so to speak, pointing in the y-axis using this grid's normals, because the normals of a geometry always are perpendicular to the geometry's faces. So let's do that by, after this grid here, wiring in a normal sop. goes in here. And now let's display the normals. And by default, Houdini creates vertex normals. However, as we want to move around points, let's set those to points here. And you can see those blue lines here represent the normal vectors of this geometry's points. Next, we painted this attribute here. I want to just switch off the normal display here. And now we will have our first encounter with scripting. Don't fret, it'll be visual. It will be VOPs, vex operators. And as we're working on points, let's drop down a point VOP, which we're going to wire in after the attrib paint. And a point VOP is something special. It is a subnet into which we can dive in and then customize and build our own small programs. So these nodes up here are pre-compiled programs that side effects designed, developed, and deemed necessary for us to use. However, if we need something custom, we can use a point VOP. Dive in there and find something like a scripting language, just node-based, with which we can build low-level functions. The first thing that I'm seeing here is a bunch of globals, and these are the attributes that Houdini by default imports into this network. So for example, a point position, a point's velocity if it has some, point's color, and point's normal. And here are the default attributes it exports: the point's position, velocity, normal, color, and force. So for now, let's just try something silly and drop down an add, and add together this point's position with its normal, and output the result to the point position. Let's go up one level and highlight this point VOP. And you can see our grid just jumped up by 1 unit. Let's ghost the underlying grid so we can see this is the translation we just did by just adding these normal vectors onto each point's position. However, that's very uniform, so we're just moving this grid up. So instead, before we add the normal to a point's position, let's multiply it with some noise to vary the amplitude with which the points are displaced by dropping down a unified noise. And unified noise is not the fastest node there is in VOPs. So for now, to dial in values, I'll use the static node and later switch it out with the normal unified noise when we're building the animation. So drop down the static in here, and this one needs a position to work. So we're going to wire up the position with our points position, and it's going to output a noise, a one-dimensional noise, so just a scalar. And this scalar is what we're going to use to multiply our normal with. So we need a multiply. Normal goes into the first slot, and the noise goes in the second slot. And now we're having this neatly undulating soft noise here. Let's dial this in a bit by setting the fractal type to terrain, setting these octaves to 2, and animating this offset by just typing in here $FF times 0.0, let's say 2. And what this expression is, it means take our current frame number, $FF, and multiply it by 0.02. So you're slowly moving along your y-axis, which doesn't do much because it's a static noise here. So again, if you set up your noise and you are confident with it and happy with it, let's switch it out with a normal unified noise using the same settings. So we're going to set this up to be a terrain of 2 octaves. Having the same offset expression in here, and then again just taking this position, wiring it over here, and taking this, wiring it into output. And you can see this cooked a while. As I mentioned, unified noise isn't the fastest node there is, so let's head up and hit play and see what this does. And not much, apparently, and that is because this expression in here does not get evaluated properly. So let's get rid of this by Shift-Control clicking in here and setting this to 0 again. What I want to do instead is promote this parameter onto our point VOP so that it's available 1 level above our very low level nodes here that we're setting up. So I'm going to go to the offset here, middle mouse on this, and go to promote parameter, and that's it. I'm going to go up 1 level again, and I'm seeing here I got this offset. So in here, $FF times 0.02. Now this should evaluate properly. And it does. You can see this slowly undulating noise here. Let's expose the controls for the noise's frequency as well. Again, diving in here, middle mousing on the frequency and going to promote parameter. And this yellow thingy here denotes that we promoted this upwards. Okay, let's go up 1 level and maybe dial back the frequency to say 0.2 along each axis. And let us hit play again. And that is fine for me now. One thing I'd like to tweak, and again, let's go in there and promote the final amplitude here, which is CC amp, I think. So middle mouse on this, promote the parameter, takes a while to cook, and then let's head up again and dialing in the final amplitude to be 5 along each axis, resulting in this. And again, let's hit play. And after a bit of caching, we are seeing this. which is nice. Why all this hassle, you might be asking? Well, if you remember rightly, we wanted to get rid of all this slow scattering, slow relaxation, and also the jittering it introduces. And the nice thing about the points after they've been relaxed, now that we scattered them onto a grid that has a normal attribute written on it, you can see when we middle mouse on those points, they also do have a normal. So instead of wiring our point bob with the noise that distorts and moves everything up here, let's wire it in after the point relax and highlight this. Hit play. And you can see we are now getting those undulating points there, which then we wire back into our attribute randomize. Let's just clean up the setup a bit, like so, and highlight the out node. Hit play again, and you can see we now have those slowly, smoothly undulating spheres there. If you guys If this question did not arise in the comments yet, let's just tackle it preemptively. How do you export your geometry to use it in other software tools? Currently, my preferred way of exchanging data between Houdini and other tools is via Alembic. And I want to point out that I'm now in Houdini Indie, as a proper Alembic export is only available for paying side effects customers. So at least you need a Houdini Indie version to export Alembic and use that in other software tools. So after we built our node tree with this undulating spheres here, in order to export this as an Alembic, I can just drop down an Alembic ROP, which is this one, ROP Alembic output. ROP standing for render operator. And the file output is regarded as rendering in Houdini as well, just rendering geometry to files. And I can just wire this in here. However, before we output everything, I just want to middle mouse on my geometry stream and check which kind of attributes we have in here. So we've got our points position, defining the mesh, got the density we painted, and the CD, the color of the spheres. And in this case, I don't need the density attribute. I just care for the color and the position. So let's delete the density beforehand using an @delete. Now let's just delete density from the points here. That's better. Now we're only left with color and the points position. Also, for some engines or some software tools, in order to recognize these points attributes correctly, they need to be on a vertex rather than on a point. So in this case, what we need to do is use an attribute promote to promote our CD, our color, from point to a vertex attribute. So middle mousing on this here reveals we now have only one point attribute with the points position and one vertex attribute called color diffuse. And now in the Alembic output ROP, first I can set my output directory to anything I want. Currently my Alembic file will be written in the same directory as my project file currently lives in, and it's going to be called output.abc. Then we might want to set this to render the whole frame range, to output an animation, and as this is only one geometry, we don't want to build any hierarchy yet. So all we have to do now is hit save to disk. And you can see this brings up our render progress bar as well as our status window down here saying how far we progressed through the export here. And that's all that's needed to export this geometry to Alembic. So while we're here, let me use the remaining time to point out a few things. You might have noticed that the last video's renders look a bit different, and that's because I'm currently trying and test driving different render engines for my premium course on rendering. And the last images and sequences have been rendered using Octane in this case. I'll attach a scene file where I set this up. If you want to learn more about rendering in general, how to set up different render engines in Houdini, again, premium course on Patreon. On the other hand, I want to point out how to help yourself in Houdini if you're stuck. One of the best features of Houdini is its help system. So for example, for the copy to points node here, what I can do is I can go to this question mark symbol here, click it, wait a bit, and Houdini will open up its help browser. It takes a while to load, and then we've got the documentation. Houdini in general is decently documented. Sometimes it's verging on the programmer side of documentation. So if you're used to reading programming language documentation, you might be used to this lingo that they're employing. However, most of the standard nodes and copy to points definitely is a standard node. They are very well documented. And you might have asked yourself, how do I know how to call a parameter on one of those template points here? So copy to points automatically scales or rotates the copies that we pipe in here. And for that, to find out, you go to varying the copies. And in here, you're seeing another link to instancing point attributes. So if you click that, wait a bit, you're being taken to this page here. And there you have a list of attributes that copy to points automatically evaluates when it copies geometry onto those template points here. And we used p-scale here. You could use a scale, in this case a vector with 3 values, to non-uniformly scale those spheres. You could use an orientation or an up vector and a normal to orient those spheres. I mean, orienting spheres in this case might not make that much sense, but if you have any geometry that is not a sphere basically. And there are a few more, so if you're interested, read through them. But this help system is available on any node in Houdini and any context in Houdini. So you're seeing this question mark symbol a lot when you're looking at Houdini's interface. And I advise you to use it. and use it frequently. Because although some parts of the documentation are a bit arcane at times, large parts of it are really helpful and sometimes even provide you with example files of how to use a given node or how to use that given node in a more complex setup. If you guys like what let's talk about one of the fundamental concepts in Houdini, that is repeating an operation over and over. Let's talk about for loops. So when looking at this image, you might be able to guess how the geometry was created, and that is by applying multiple extrusions to a single cube. Let's talk about how we built this by dropping down a geo node in Houdini's OBJ context, diving in there, and then dropping down a cube, or a box as it's called in Houdini. By default, this has one polygonal face per side. We can also set this to be a polygonal mesh, so it has multiple polygons per side. Now what I want to do is I want to use the poly extrude to select a few faces and then extrude them. So let's highlight this one here and let's increase the distance. And you can see this extrudes all the faces simultaneously. However, up in here in the group field, I can type in either the number of a given primitive or a list of given primitives like so, or I can type in the name of a group, which we haven't created yet and doesn't exist, or an expression, as I've shown you in a previous tutorial. Let's use this expression workflow to select random faces here. Namely, what I want to do is create an attribute with a random value. So again, let's use the attribute randomize, drop that down, wire it in here, and let's set the attribute to be on primitives. That is the polygonal faces here. And we don't want the color CD to be randomized. And also we want this to be only a float and not a vector with 3 components. So let's dial this down to only 1 component and call the attribute maybe this, or let's call it active. And also, I don't want the random distribution to be uniform, but to change between 2 values, namely 0 and 1. And let's set the probability for this value to be 1, to say 20%, 0.2. Let's go to the geo spreadsheet and have a look at this. So under primitives here, we have this active value, which is either 1 for these few primitives here, or 0 for the rest of them. So let's check if this value is 1, down here in the poly extrudes group field here, by typing down @ to access our active attribute, and if it is exactly equal, that's what these 2 equal signs mean, to 1, then we want to extrude this. We can see now we randomly selected a few faces that are being extruded here. One thing I'm seeing here is this. Let's just disable the grid. So instead of just extruding those individual faces down into the side, they are joined here. However, I only want those individual primitives to be extruded straight. So let's set the divide into individual elements, like so. Also, what I want to do is I want to randomize how far those individual faces are being extruded. And the poly extrude has a tab called local control, where I can specify an attribute that scales this distance here. And it's called zscale. So let's create a random attribute on our primitives as well, called zscale. And in our case, again, let's use an attribute randomize. Wire this in maybe before this one, call this zscale, set its dimensions to 1, and set its attribute class to be on the primitives. So now immediately you can see we're getting these individual extrusion lengths here. And I can just increase the distance to say 1, or maybe set it to 0.4 or 0.5. Okay, so these 3 things here. If I want to repeat this step, what I of course could do is copy these 3 nodes, pressing Ctrl Z and then Ctrl V to paste them again, and then wiring them up down here. And when we change the output from the first extrude to the second extrude, we can see that's doing exactly what we want. Maybe in here in both attribute randomize, under the options tab, let's change the global seed, so the seed changes between those individual extrusion steps and gives this a bit more of a random appearance, like so. I could do this over and over again until I have a really long node chain and arrive at the result that I envision. However, imagine that I just want to dial in the overall extrusion distance here for all these steps. I would have to select each of those individual extrusion nodes I've created and dial those values in individually. And also copying and pasting for each new extrusion that you want to do is kind of cumbersome, right? So let's get rid of those 3 nodes and enter the for loop. So if I start typing for here, I can see down here the for loop with a feedback, which drops down this construct of 2 nodes and this frame around them. Let's just cut this connecting line in here by keeping Y pressed, which turns our cursor into this scissors symbol, and then just clicking with the left mouse button, keeping it clicked and just cutting through this wire. This is our for loop, which basically does nothing but take an input geometry stream, apply the operators that are within the loop, and then at the end output the result and feed it back into the loop a given number of times, namely how many iterations we dialed it in. So for example, in this case, 10 iterations. Let's reset that to 1 iteration and wire the first node up here after the box and the second node after the extrude here, and highlight the second extrude. Nothing changed. We are running this whole loop, only 1 iteration. However, let's increase the iterations and we can see we are successively extruding other faces. One thing we are currently not doing, however, is change those seeds so they stay the same for each loop, which is somewhat fine because our primitive count, our poly count is changing, and thus the primitive numbers are changing as well. So it's highly unlikely that the same primitive face will be extruded over and over again. However, just to be sure, I want this global seed value to change each iteration. So we need a way to let the seed know in which iteration we are. And to do that, it's a bit cumbersome, but let's go through it. On the repeat begin node here, there's a button called create meta import node, which creates this third node. And when you middle mouse on this, you can see this node has a few attributes, namely iteration, I value, num iterations, and value. And in the iteration or I value, we store which iteration we are in. So the I value in this case would range from 0 to 9, and the iteration would go from 1 to 10. Let's just use the iteration here to set the seed directly. In this case, I'll need to use an expression to access this value here. So this, again, if you middle mouse, is a detail attribute. And the way we access this in a given field in Houdini is with an expression called detail. And this takes a few parameters. First, it takes the path to the node from which it should derive the detail attribute, in this case this one here. And this is the relative path. So currently, again, think of Houdini as an operating system and this as a tiny program running. We are in the, so to speak, folder of this program. So let's go up one level by dropping down point and the /. If any of you ever used DOS or Linux, you know this syntax. And now Houdini automatically offers me an autocomplete. So I'll just start typing repeat begin metadata 1. That's the node we want to access. Then drop down a comma, and this is Houdini's automatic help here. So it takes the first string, which is the path to the node, the second string, which is the name of the attribute, and then a float value, which is the attribute's index. In our case, as this is only a single float value, we can set it to 0. So the attribute's name we want to look up is iteration, and its index is 0. And now this is green, so it means it evaluates correctly. We can click on the name here and see the last value that we had. Let's just click on this again and copy this whole expression. Go down here to the attribute randomize 1, and under options, just paste this, and maybe for good measure, add some value to it, like so. And now we can easily dial in the number of iterations here, and also easily dial in the distance by which we want to extrude, or maybe the probability of a face being extruded. So the lower we put this, the lower the probability of a face to get extruded. If you guys like what we're doing and want to support us, you might want to head over to our Patreon, and we'd like to thank all of our patrons, especially Refik Anadol, Chris Hebert, Important Looking Pirate. So hello and welcome to one of the first Houdini tutorials. And for this tutorial I've prepared something special that is quite difficult to do in other tools, but in Houdini is really straightforward. And what we try to do today is this dent here, a dented look, which has become quite popular over the last months, over the last year. For example, it's been done in this intro animation here. So really quite nice, and I want to show you a really straightforward and easy way in Houdini to do that. And in order to accomplish that in Houdini, we are going to use volumes and Boolean operations on volumes. So let's see what we're going to do. What we want to achieve in the end, and I've called this process Boolean Denting because I want to do those dents, and we're going to do some Boolean operations to accomplish those. So what I want to have in the end is something like this, where just one object looks like it's been pressed into another object. And the way we're going to do it is like this. We start with both objects, which are just intersecting each other, and then we expand one object, first the intersecting object, and then we expand the second object. So we have just those two basic objects that have both just been grown to this darker red and this turquoise color. So we have something like this. And the next thing we're going to do is we intersect both of those grown objects and keep the intersection area. So we end up with something like this. This is the newly formed intersection area. And again, the way we did it is just take the two basic objects, grow both, expand both, and then intersect those. So from this area that we just generated, we'll subtract the original object and merge it with the bigger object that is intersecting. So we end up with something like this. And the final step we have to do is just basically blur out those corners, round those corners, soften those corners, and we're done and have a geometry which in theory should look like that, like the light blue area here. So let's dive into Houdini and build this. First thing I want to do is create a geometry. Dive into the geometry. Delete that, and just gonna use two spheres for that example. So let's create a sphere. Let's set its type to polygon. So we just get a regular polygon mesh and increase its subdivision. I'll copy that. And first thing I want to do is just, this should be a smaller sphere intersecting into that sphere, and I just want to ghost that sphere so I can see it while working on that. And I'm just gonna make it a bit smaller and move it up. Yeah, something like that. So in order to do all those Boolean operations, all those merging and intersecting that I've shown you in Illustrator, it is necessary to convert the geometry into voxels, into a volume. And the way you can think about voxels or a volume is basically they are what a Photoshop file is in contrast to an Illustrator file. So what we have now would be an Illustrator file. So just loads of vectors, loads of polygons, loads of basically lines, loads of basically tiny lines that form up a geometry. And a volume, in contrast, is formed out of tiny little voxels. And the way you can think about it is just like they're tiny little cubes that are kind of 3D pixels. So, and those really make it easier to do operations like Boolean intersection, Boolean union, or example, smoothing out stuff. So let's convert our geometry into volumes. And we do that by VDB from polygons. And a VDB is a volume database, and VDB is just a special way to represent a volume. It's really fast, it offers loads of features, and if you can, you should try to stick to VDBs for volumes in Houdini. So wire this up, highlight that, and we see already those tiny little cuboids. Those are too coarse for me, so I'll go into that node and change the voxel size down to something smaller. That's better. Okie doke. Copy that node, paste it, and wire up the second sphere as well. So I now have the big sphere and the small sphere, both as volumes. Cool. So the next thing I'd like to do, I'm just gonna go back to the drawing again, is expand both the smaller sphere and, in this case, the bigger sphere. So the way I'm gonna do that in Houdini is with a node called VDB Reshape. VDB Reshape SDF. And an SDF is just a representation of a surface. Manuel is going to go into detail about that if you want to know more, but for the moment, for the time being, keep in mind SDF is a surface of a volume. So wire that up, and voila. So this is the previous geometry, and this is after the reshape. So what the reshape does, it's dilating it, and dilating a volume means expanding it. So as you can see here, this is the original volume, and this is after reshape. It grows a bit, and I want to make that a bit more extreme. Let's maybe grow it by, that's too extreme. Grow it by 4. And the offset here is specified in volume, so we just enlarge this thing by 4 voxels. Let's do the same thing for the big sphere as well. Again, this is before, this is after. So now we have both geometries expanded, and the next thing we want to do is intersect both of these objects so that they only keep this intersection area. And that also is pretty straightforward in Houdini. The way we do it is by a node called VDB Combine. And we wire up those two inputs, highlighted, and within the node, you can select which operation it should perform. So basically what we want to do is an intersection, an SDF intersection, because again, SDF is like the surface, like the outer surface that we want to work with. So let's choose SDF intersection, and we see we have an intersection area of this and this. So that's the intersection area. So next thing we want to do is subtract the original small sphere from that intersection area we just created. So we end up with something like this. So let's just do that again with a node called VDB combine. And we want to do an operation which takes that and subtracts the small sphere. So that minus the small sphere. So let's wire up that on the first port, minus the volume of the small sphere, and set it to difference. Difference just does port 1 minus port 2. So what we did now is, let's disable the ghosting here. What we have now is exactly that shell. Okay, put it here. So now what we want to bring back is the outer part of the big sphere. So basically that. But I want to like subtract the outer part of that. So let's do a VDB combine again, and I will take the big sphere and subtract this outer shell from it. Again, highlight it, dive in here and say SDF difference, and have like the outer shell subtracted. Oh, and of course I don't want to have that on the enlarged sphere, but on the original small sphere. So let's do it like that. Exactly, and I have now those two. Now I'm going to merge them and do that by VDB combine again. Wire up both of those geos into that node and do an SDF union. So I end up with that. So this is already quite nice. Now the only thing I want to do is kind of soften that edges so they become more organically looking, more soft. And this is done by a VDB smooth SDF node. I just wire it up here, and now and what that actually does is it works like a blur in Photoshop. So it blurs voxels and softens boundaries. So exactly what we want. So now that we have this geo, we can convert it back to polygons in order to, for example, render it or do other geometry operations, geometry fun with it. I'm going to do that by a VDB convert. Wire it up, highlight it, and convert it to polygons. So now I have back my polygon object. So let's see. Let's merge that again with the original sphere. Do a merge node here, our indented geometry and the original sphere, and highlight that. And we now have a sphere that dents into another sphere. And the beauty of this operation is that it's fully procedural. So what I can do now is, the easiest thing that I can do is, for example, move that sphere a bit, and the other geometry will automatically react to it. So this is already animation ready. Or I could change that geometry going in there. So for example, exchange it with a platonic. To make that easier, I'll just exchange that with a null, so I don't have to constantly rewire. So exactly like that. And gonna put that into here. Make it a bit smaller. Move it upward. So now I have a platonic object pushing into that sphere. Also, what I could do is go back to the sphere again. I could, for example, build something like a cloner. Come here. points on the other sphere, not so many, maybe only 20, and copy that sphere onto those points. I have to reset the translation, exactly, and wire that into my null. So now I should end up with, yeah, a sphere with really lots of dents. So quite a versatile setup, really straightforward, just to give you an idea what's possible inside of Houdini and what's possible with procedural setups. So what we'd have to do now is export that geometry and render it, or even render it inside Houdini. And the way you would export geometry in the non-commercial, in the apprentice version of Houdini, is you can only export a single geometry file, so no geometry sequences, but for most experiments we do, this is enough. So the way you would do it is right-click on a node you want to export and say save geometry, and then just give it a name, and it automatically checks which file you want to export it to. So I usually do an OBJ or an Alembic. So if you put OBJ on it or .abc for Alembic, you can export it. So I hope this whets your appetite for more Houdini stuff, and I hope you stick around with us and accompany us on this route down the procedural highway. So cheers and see you soon. After we published the VDB denting tutorial, I've been asked how I created these abstract shapes that I used in the preview image for this tutorial. So let me just quickly show you how. Start out by creating some geo, for example a sphere. Dive in there, turn the sphere into polygons, and with the ISO offset quickly create a volume out of that, like that. Then, using the scatter sop, scatter some points into that volume, not so many, but maybe say 50 to begin with, and then connect these using the connect adjacent pieces sop here. Wire that up, and what that does is it works pretty similarly to the Vex setup that Manuel did. Just have to set it up to adjacent points and let's decrease the maximum number of points it should connect and increase the search radius, and as you can see that builds a network like this, a network-like structure. Like that. Let's dial down the maximum number of points again, and maybe in the scatter sop use a little less relaxed iterations. Something like that. And now let's turn this into a volume by first adding a wireframe sop to turn the splines into geometry. Maybe lower the radius a bit. Maybe like that. And turn that into a volume with a VDB from polysops. Wire that up here, highlight it. Increase the resolution by decreasing the voxel size, like that. And use a smooth SDF node to blur out the whole geometry a bit. Maybe to something like this. One thing that's lacking here are the bulges on the joints here. And I'm going to add them by using a copy sop and copying a sphere onto those scattered points, like that. Let me just set the sphere to polygons as well, maybe increase the frequency a bit and scale it down. So we'll just have that here. And before turning that into a VDB here, let's merge it with the wire. Just using a merge sop. Merge those two like that. And then wire that up into the VDB from polygons. Let's dial down the sphere size a bit more, like that, which will yield this VDB, and after it's smoothed, will yield something like this. So this is the base shape. We could increase the smoothing iterations a bit, and also maybe decrease the sphere radius still a bit, something like that. Exactly. So this is our base geometry that we're going to work with. Next thing I'm going to do is convert that VDB back to polygons with the convert VDB sop here. Wire it up, set it up to polygons, and what that will give us is this polygonal shape. And as you can see from the algorithm which is used to convert the volume back to polygons, it yields this kind of strange mesh here. And in order to fix that, I'm gonna add a remesh node. Wire it up here, highlight it, and what the remesh node will do here is give me more like a Delaunay triangulated mesh, something like this. And the last thing I have to do now is, again with the wireframe sub, and let's dial that radius down quite a bit. Wire it up, highlight it, maybe dial the radius down a bit further, like that. And this is how I created the structure for the preview of the VDB denting tutorial. So that was rather a quick tip. Hope you enjoyed it. Again, if you have artwork to show, please do so. Very intrigued to see what you guys come up with. If you have any hints on how to improve the setup, please share those as well. Have fun, cheers, and goodbye. And that is actually... Last week we posted this image of what looks like hairs floating in outer space or in zero gravity. And the reason this image came to be was from a question that we got from a comment on Vimeo. And the question was, how do you color trails and strands in Houdini? And that is actually straightforward. But before we do that, let's talk a bit about what's happening here. Let's talk about how we created those individual strands, those lines. Let's talk about advection. And the type of advection that we're actually doing here is called point advection. And we advect the point through a vector volume. So to simplify things, instead of looking at the whole volume here, let's just look at one slice out of the volume. So this grid is just like, imagine it like a slice through a giant Rubik's cube. And each one of those cells in reality is like a tiny, tiny cube. And within those cubes you can store values. In our case, we store vectors in those cells. And the way you can think about vectors is just arrows pointing in a certain direction, and those arrows have a certain length. What we do now in order to advect a point through this volume is we just pick a start position for our point. In our case, I've drawn this slightly bigger orange circle here, so let's look at that point. And the thing we do is, from that point's position, we look at which direction are the vectors pointing in. So in our case, it's pretty straightforward. We only have to look at this vector. But for example, if the point would be in between some vectors, usually there would be some interpolation happening. So we, for example, would look at the closest voxel storing a vector and average them out, for example. And the whole process of looking up that vector is called sampling. So what we do is we sample a vector from this point's position. And the next thing we do is move the point into the direction we just sampled, but just for a given amount. So this, in our case, would yield this new point position. And what you do then is, from this new point position, do the same thing as previously. Again, sample the vector position from the vector field, and then move the point into that newly sampled direction. And you just repeat the process over and over again, and thus move a point through a vector field. So basically, point advection is just moving the point through a field of arrows pointing in the direction where the point is going to move. Inside Houdini, the way we're going to build that is by dropping down a geo node first, diving in, and then dropping down, for example, a grid. And this grid should be the start position for our points that we're gonna advect through the volume. So let's just scale it down a bit, and let's scatter some points on it. Just like that. Let me disable the grid in here so we can see those points that we just scattered. The other thing that we need for point advection through a vector volume is a vector volume. So let's create that. And the slightly quicker way to create that volume is with standard Houdini volumes. It is quicker to create, but it is not necessarily quicker in its computation. But for our example, we will keep the volume rather small, so shouldn't be a problem. So let's create a volume with the volume node. Let's just highlight it and ghost this here. And within the volume node, we can just set up a given size for the volume. So let's make it 4 by 4 by 4 units. And in here, we can input the uniform sampling divisions. And what that will give me is the divisions this volume will have. So now it will be a 10 by 10 by 10 Rubik's Cube. And I need a bit more resolution. So let's increase this to, say, 50 by 50 by 50 voxels. So 50 by 50 by 50 cubes. The next thing we actually need to do is tell this volume to contain vectors. So we do that by setting its rank to vector. So instead of just a single number called a scalar, it now contains a vector, which is 3 numbers, defining that arrow pointing into the direction. We also have to give the volume a name, and in our case, we just call it vel for velocity. Now that we have this volume, we need to fill it with vectors, because now all of its cubes are filled with zeros. So let's drop down a volume bob, wire this up, dive into the volume bob, and let's fill the volume with something. In order to generate a field that looks like a flowing liquid, we can use the curl noise. And if you remember that, we already used that in another video tutorial. The way we're going to use it is just drop down a curl noise here, wire up its position. And in order to export this to our volume, which is called velocity now, vel if you remember, we have to use a bind export node. So this will write values into the volume actually. Let's just tell it to write into the volume called vel, and the type should be set to vector because we want to write out vectors. And now what I can do is just wire up the curl noise output into that bind export, and that should be it for now. Okay, now we have points. Now we have a volume. Let's select them. There are several ways I could do this, but in the end what I want are those strands that look like hairs, those kind of trails. And there's a really handy sop for that, and it's called the trail sop. The volume trail actually, not the trail sop. So what it takes is the input points to trail, so let's wire them up here, and it takes a velocity volume that we just created here, and we also called it velocity. So as soon as we highlight this node, we see we created strands that are flowing through this vector curl field. Okay, but what about those crazy colors? We just want to colorize them the way we like, so let's just get rid of those fancy colors. This can be easily done by just unchecking visualize velocity, so the trails get all black now. Also within the sop, let's highlight the points. What I see here, those points are pretty sparse, so the resulting trails get like these sharp angles in here, those corners here, and I don't want that. And the way to get rid of them, to increase the sampling density on those trails, is if we got use CFL checked, let's just decrease the CFL value, and thus the point distance gets smaller and smaller. Something like this. Okay, now we have some nice trails sampled in here, and how do we go about coloring them? So first, let's import an image in here to color those points. So let's drop down an attrib from map node and wire that underneath the grid and highlight it. And let's increase the grid's division a bit to say 100 by 100 so that we see actually something. And if you remember the Poly Rembrandt tutorial, for example, we used that node to just quickly load an image onto a plane, and we're doing the same here. So let's just invert its V, so the image is upright. And let's select another image. Let's say something by Klimt this time. When we go back to our volume trails now, nothing has happened so far. And that is because the trails don't inherit the color values from their original points. So the way we're going to fix it is by using an attrib promote. Because when we click on that node here with the middle mouse, we can see what we created are primitives now. So each one of those trails is a single primitive. And what we can do now is, when we highlight the volume trail and go to the geometry spreadsheet, we see that each point in there has its individual color. What we see is those points coming in from the plane, those points that we originally scattered on the plane, they do have in fact the plane's color here. However, the colors of the trail's newly created points are automatically set to 1. So let's use that knowledge. let's use that knowledge and think about how we can use it to actually color the whole trails. And the idea behind it is we know that all those newly created points have a color value of 1. So what we're going to do is we just look for the lowest color value and use that to color the whole primitive. And it can be done with the attrib promote sub here. So let's wire it up, highlight it. And what we want to do is we would like to promote the color. So that's the CD attribute. And we want to promote it from a point to the primitive. The way we want to do it is we want to promote the smallest color value for each primitive. And that is done by selecting minimum as the promotion method. And boom, what you see is we have now colored strands with the color from the original scattered point. So let's increase those points a bit to say maybe 10,000. And we see we get those really nice structures that keep the value of the original point and just trail it through the volume. And what I want to do now is render this. So let's dive up one level and create a camera by control-clicking on the camera icon. Let's lock this camera so we can move it with the viewport. And this time, let's just light this with 2 area lights. So let's click on area light and just drop one down here. And let's transform it, zero it out, just rotate it down 90 degrees and move it up to, say, 4. Also, under the tab light, let's increase its area size to say something like 3 by 3 and duplicate it. Move that down like so, rotate it so it points upward and increase its size even more to say 12 by 12. So we have a really broad light coming from underneath the structure. And let's dial down its intensity to say 0.3. Okay, one thing we need in the output is a mantra node. So to render this, and under rendering, I'm just going to set it to physically based rendering. Okay, let's go to render view. We have our output node selected. Let's just make sure we select the cam1 and hit render. Okay, several things that we see. The first, it's a bit dark, so let's just go to the OBJ level and increase the area light's brightness. So let's say we increase the top light's brightness to something like 10 and the bottom light to maybe 2. Okay, better. Now I see those strands are a bit thick, so we can fix that by going into our original geo where we created those strands, and after the attrib promote, we just attach an attrib create node. Wire that up, and in this node, we're gonna create a point attribute of the type float, and we call it width, like this. And let's set it to something small, for example, 0.01. Highlight this, and we see our strands got smaller. So as soon as you have trails or polylines that have an attribute called width, Mantra automatically knows that this is the width of the strands. Let's decrease this a bit more. However, there are still several things that are bugging me with this. On the one hand, those strands, when I increase their size again, it turns out they don't really look like round strands, but more like flat ribbons. And this is because Mantra actually regards those strands as flat ribbons. So we have to do something in order to make them appear round. One thing, of course, we could do is just drop down a polywire or a wireframe sub, but that would generate geometry. And geometry usually is very resource intensive to render. So instead of that, let's decrease the size again and fix it with a shader. Because the one thing that we didn't do yet is apply a material to the object we created. So in the shop, in the shading network, let's just drop down a Mantra surface here. And in the OBJ level, let's just give our geo that material, like so. Let's go back to the material that we just created. And in this material, let's check that it uses the point colors. And let's set the base color to pure white. Okay, but still, these look like flat ribbons. The way we can fix it is by right-clicking on the mantra material and clicking on Allow Editing of Contents, which will actually allow me to dive into that shader. Let's make this a bit bigger. And we see this beast is the whole mantra shader. And the only thing I need to take care of in order to make these flat ribbons appear roundish is with the base normal and the code normal, attached to it a node called hair normal. And this will fake the normals to look like a cylinder, to look like a hair, to look like an actual rounded strand. So let's just wire them up here and here. Let's move this over again. And we can see now they have this round appearance, like hair or like strands or like extruded cylinders. What we did actually is hack the mantra surface to behave like a hair material, like a mantra hair material, but instead have all these nice presets. So what we can have here is best of both worlds. On the one hand, we have a shader which allows to quickly shade strands. On the other hand, we still have the powerful mantra surface with all its shading parameters that we're used to. So what we can do now is go back to our object level, and in our geo, on the one hand, maybe increase the amount of points scattered in here. So let's say 100,000 points. Maybe decrease the width a tiny bit, say to 0.003. I think it's getting a little too dark on the bottom part here, so let's check with the bottom light. Say something like 10, and increase the top light's intensity a bit as well to 20, so we bring out the colors a bit better. So the main parameters for this setup in our geometry here are, on the one hand, the settings that you have in here in the volume WOP with the curl noise that you generate, because this drives how the paths will form by just advecting the points to the volume. Just play with those parameters. They offer a plethora of possibilities and ways to influence and create your image. On the other hand, you can play with the settings in the volume trail. For example, if you set the advection method to be advection by time and not by distance, those strands will have different length, which will make them look a bit more organic. If you decrease or increase the maximum steps number, that influences how long those trails get in general. And of course, there is no need to scatter those points on a plane, but you can scatter them on any geometry you like and use any image you like. So I'm really looking forward to see a wide variety of artworks from you guys. That's it. That was a quick one. I hope you enjoyed it. Again, if you create any artwork, just shoot us a link. We are very eager to see what you guys come up with. Hope you had fun. So it's cheers and goodbye.